So hello everyone and welcome to this next lecture. So in the previous lecture we had reviewed capacitors and inductors as filter elements, and we had talked about their properties and why due to their properties they are very popular filter elements. Now in this lecture we are actually going to talk about analog filters, how inductors and capacitors are used to form analog filters. So this figure on the left is one of the most common low pass filters that are used in most circuits, right, including power electronic circuits, and this is called an inductor capacitor filter, or simply put an LC filter, right? So you have the inductor, you have the capacitor, you have the input voltage here, and the voltage across the capacitor is typically the output voltage, right, the output of this stage rather. I will talk about that soon. Now to understand how this works, you just have to write the equations, right? So the equations are pretty simple. The inductor, as we already said, the current through the inductor has an integral relationship to the voltage across it. So the voltage across the inductor is the difference of the input and the output voltage. So this is the equation. You have the integral equation. The voltage output, right, output voltage, which is the voltage across the capacitor, now has an integral relationship with the current through it. So this current, which is now flowing, is going to flow through this capacitor, assuming of course we don't have an output. We have an output, there will be some flowing across this as well, but this is the integral relationship, right? So what you have again here is the result is the output voltage is an integral of the current, right? Now let's continue for now. Now as I've already said before, the reason when you have an integral, the nature of the integral is to smoothen your waveform, right? So even if the input has a high frequency noise, the integral of Vn minus Vo will be a smoother waveform, because in integration is an accumulation over time, and when you accumulate over time, the smaller fluctuation gets smoothened out, right? So the result is, because of this integral action, even if Vn has high frequency noise, the current is going to be much smoother than the input voltage, right? It will still have some noise, but the noise component is going to be much smaller than the input voltage. That is the reason, that is the nature of this integral. Now, this is the reason. Now, what actually happens is that the output voltage, the output voltage is another integral of the current. So actually there is a double integral taking place. So this inductor current is further integrated to produce the output voltage. So this is the output voltage with respect to the input voltage. It's a double integral. There is the integral of the difference of Vn minus Vo, and that is further integrated to form the output voltage. It's just combining these two equations, right? Now you can pretty obviously see the integral by its nature has a smoothing effect. The double integral is going to have a doubly smoothing effect, right? So the result is this output voltage is going to be much smoother than the input voltage, and this is by a factor of 2 because of this double integral. So this is how this inductor capacitor works. This inductor capacitor can take an input voltage with a significant noise component and produce an output voltage that is pretty smooth, right? And this is because of the nature of the inductor and capacitor. Quite simply put, this inductor will try to block any high frequency noise or high frequency components in the current, and the capacitor will bypass any high frequency components in the current and produce a smooth output voltage. This is the nature of this inductor capacitor filter. I would suggest just go back to the previous lecture and review what I taught there to be able to understand this better. Now let's look at this last equation in a little better. So I have blown it up in this manner. This is the complete relation, that is, this is the complete equation that relates the output voltage to the input voltage. Of course the output voltage also appears on the right hand side. Now such an equation can be solved, right? There are ways to solve it. You can solve it analytically. So there are mathematical techniques such as substitution and various things which you can use, and you can actually solve it to get an expression with respect to time. Now you can also solve it numerically, right? So it is iteratively over time, and eventually you will see that as you just have, like, time keeps on incrementing and you develop a waveform of this voltage with respect to a certain input voltage. So there are two ways to solve it, right? Now the problem with the numerical solution is that, or rather the analytical solution is that quite often we don't just stop with just one LC stage. It's quite normal that you stack them up. So this is a one stage, To this you add another stage, just a similar LC, and sometimes you keep adding stage after stage after stage depending on how much filtering action you need. So it is quite common to stack LC filters to increase the filtering action, right? Now the problem with that is, as you increase the number of stages, this final output with respect to the input is going to have so many double integrals, right? So if you have 4 stages, you will have 8 integrals. Now at this stage, an analytical solution becomes very cumbersome. Alright, you could do it, I'm not sure, there may be techniques, mathematics is pretty advanced in those cases, but in such cases usually you end up going to numerical solutions. Alright, so you want to know how it behaves, you just solve it numerically. Now there is nothing wrong with a numerical solution, it's quite okay. The problem is that an analytical solution doesn't just give you the result, it also gives you a theoretical perspective about any system, which is actually quite informative. It tells you a lot about the system, right? It tells you even properties about the system that a numerical solution would not be able to provide. Alright, so now the question is, how do you continue with this analytical solution in such a case? Now, and this is where I lay the foundation, or rather the need for what is called as transformations. Right? The way to continue on the analytical path is through transformations, and we will talk about this in the next lecture. So as before, I'll be stopping this lecture right now. If you have any doubts, please do post in the Q&A forum and I'll be happy to help you out. Otherwise, I will see you in the next lecture. Thank you so much and goodbye for now.